And now we will learn how to solve some gas stoichiometry problems. These calculations combine two of your favorite concepts, gas laws and stoichiometry. Let's first review the normal approach to a stoichiometry calculation that involves gases. So far, all of the gases we've looked at were at STP, or standard temperature and pressure. And so we've always used this ratio, 22.4 liters per mole. This allows us to go from liters to moles, or moles to liters in our calculations. So here's how we've solved our gas law problems up to this point. How many liters of sulfur dioxide will be formed when 40 grams of sulfur trioxide decomposes? Assume all gases are at STP. So we write the given 40 grams of SO3 over 1. Next, we write the unknown units, liters of SO2. And then we fill in conversion factors, going from grams SO3 to moles SO3. Next, the mole-mole ratio. And finally, we convert moles into liters. And we learned that at STP, any gas has a molar volume of 22.4 liters. We'll cancel the units and simplify the numbers to get 11.2 liters. We've done this type of calculation many times before. Nothing new here. However, most gases are not at STP, and these situations will be a bit more complicated. That's because we can't use that last conversion. So we'll still go from grams known to moles known, and then use our mole-mole ratio to get moles of unknown. But at this point, we'd need a different formula, the ideal gas law, or PV equals nRT. We can do this because in our stoichiometry calculation, we found N, or the moles of gas. So our approach to this problem is to first use stoichiometry to find the moles of unknown, and then we'd plug that into PV equals nRT to determine the volume. Let's try an example of this. What volume of oxygen at 350 kelvins and 820 torr should be produced when 245 grams of potassium chlorate decomposes? Notice, this gas is not at STP. I like to begin my calculations by identifying what I'm looking for. In this problem, it's the volume of oxygen. I would also note the temperature of the oxygen is 350 Kelvin, and the pressure is 820 torr. I'm also told that there are 245 grams of potassium chlorate. So you might solve this like a stoichiometry problem. I'm given 245 grams of KClO3. I'm solving for liters of O2. Then I fill in conversion factors to go from grams KClO3 to moles KClO3. Then moles KClO3 to moles of the unknown, oxygen. And finally, moles of oxygen to liters of oxygen. But wait, I can't use this conversion factor because the conditions are not STP. So here's how we'll solve this. We skip the final step, instead calculating the moles of O2. A few simplification reveals that we'll make 3 moles of O2. So we just found the variable N, or the number of moles. Now all we have to do is plug each variable into PV equals nRT. We'll solve this equation for V and substitute numbers. Remember, R is always 0.0821 atmosphere liters per mole kelvins. A close look at our numbers shows another problem. The pressure units are different. I need to convert the pressure measurement. 1 atm is equivalent to 760 torr. So I calculate the pressure is 1.0789, etc., ATM. I'm going to write 1.08, but when I calculate, I'm going to use the full number to be more accurate. And now all the units will cancel, leaving us liters. And 3 times 0.0821 times 350 divided by 1.0789, etc., gives us 79.897 blah, 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 which will be rounded to 3 digits, or 79.9 liters. So we did 2 calculations to solve this. We began with a stoichiometry calculation and calculated the moles, or N, of the unknown gas. Then we used the ideal gas law, or PV equals nRT, to finish up this calculation. In addition, we had to perform a conversion problem. There's another type of problem that you might have to solve. One where you try to calculate the mass of a material, starting with the volume of a gas that's not at STP. You can't start this problem using the conversion 1 mole equals 22.4 liters. Instead, you'll have to use the volume of the gas along with its temperature and pressure to determine N, or the moles of the gas. From there, you'll complete a shortened version of a stoichiometry calculation, going from moles of known to moles of unknown, and then to grams of unknown. So for these calculations, we'll start by using the Pivnert equation to find the moles of unknown. Then we'll do the stoichiometry problem. Let's try one. How many grams of carbon are required to react with 640 milliliters of oxygen at 47 degrees Celsius and 2 ATM? We're looking for grams of carbon, and we're given 640 milliliters, or 0.640 liters of oxygen. Oxygen's temperature is 47 degrees Celsius, or 320 kelvins, and its pressure is 2 atmospheres. So we have V, T, P, and we always know R, which is 0.0821 atmosphere liters per mole kelvins. So we can calculate N, or the moles of oxygen. We'll write the ideal gas law, PV equals nRT, and then solve for the unknown, N. N equals P times V divided by R and T. We plug in the values, 2 ATM times 0.640 liters divided by 0.0821 atmosphere liters per mole kelvins, also divided by 320 liters, and all units cancel except for moles. Calculating, this gives us 0.04872, etc., moles. But remember, we're looking for the grams of carbon. So we'll use 0.0487 moles of oxygen to do a shortened version of a stoichiometry problem, one in which we start with moles instead of liters or grams. So the next step is the mole-mole ratio, and then we convert from moles to grams. All units cancel, leaving grams, and the calculated answer is 1.169, etc., which we round to 2 significant digits, or 1.2 grams. So we've solved 2 examples of the types of gas stoichiometry problems you may see. Good luck with your calculations, and have fun!